the optical activity, which we'll talk about. Before we get into the optical activity, we need to talk about how we can differentiate between these two mirror image molecules. How do we know we're talking about the first molecule and not its mirror image, or the mirror image and not the first molecule? So there's an extra little piece of nomenclature, kind of like we did with cis and trans ideas. We went different from our previous examples of stereoisomers. So this is what is sometimes referred to as the Kahn-Ingold nomenclature system. And once we've sorted out the name of the compound, the core name, we're going to do a little bit of work right at the beginning of the name based on the spatial arrangement of the groups around that chiral carbon atom. So, wherever there's a chiral carbon atom, we're looking at the groups which are attached to that chiral carbon. Looking at the four groups which are attached. And we're going to prioritize them. We're going to prioritize those four groups attached based on the relative atomic number. The higher the atomic number, the greater the priority. So we have around that group of hydrogen, carbon, bromine, and chlorine. Bromine is the highest atomic number, that'll be given the highest priority. Then chlorine, second highest atomic number, then carbon, then finally hydrogen lost, only an atomic number of 1. If we can't get clarity in this way by atomic number, then we look for maybe a heavy isotope in the mix. Maybe a heavy form of oxygen, like oxygen 17 instead of 16, or maybe hydrogen 2, deuterium instead of normal hydrogen, a mass of 1. And if we still don't get clarity for the groups which are directly attached to the chiral carbon, then we're going to look down the chain, comparing atom for atom, until we find a difference in the atomic number. And that will therefore lock in priority for the four chains from 1 to 4. Let's look at some examples. So there's a non-superimposable mirror image pair of enantiomers, and it's the carbon in the middle here, which is the chiral center with 4 unique groups attached. And we'll prioritize the 4 groups. So the chiral carbon sees a bromine, a carbon, a hydrogen, and a carbon, as does its mirror image molecule. We'll prioritize those 4 groups, those 4 atoms directly attached to the stereo center. Lowest priority to the hydrogen, third place carbon, first place the bromine. Oh, actually there's 2 here. So there's a tie here between between places 2 and 3. Bromine is definitely the winner because it's the highest atomic number. Hydrogen is definitely the loser because it's the lowest atomic number. And we'll look at the groups attached. So carbon to carbon, and because we have a tie, we then look at the atoms which are attached to those carbons, giving us a tie. Move this up for a second. This is what we were talking about. Move this down a tad. So let's see what we've got attached. Comparing these 2 branches, we've already seen the carbon on this chain. And what does it have attached? It has a hydrogen, a second hydrogen, and also a chlorine atom. We look at this chain, it's removed slightly from the molecule. From that carbon, we see 3 hydrogens. So we've already compared carbon to carbon, which gave us a tie. From this point, there's always 3 atoms attached as we move down the chain. So we're looking at atoms which are 1, 2 atoms, 1, 2, 1, 2, 2 atoms away from that original stereo center. 1, 2, 1, 2, 1, 2 atoms away from the original stereo center. And look at the priority amongst those 3. highest priority is the chlorine. Highest priority of the three here is just one of those three hydrogens. Chlorine wins over hydrogen, so this entire branch is given second place. So we're comparing the atoms in the chains, and if the first atom doesn't give clarity, doesn't give higher priority, then we move down the chain in sequence, looking for the first occasion where there's an atom of higher atomic number, and therefore higher priority. 99% of the time, we'll just be looking at the very first carbon or the very first atom in the chain. So, we'll give it priority to the four groups attached. And with the mirror image molecule, the prioritization is exactly the same. Bromine first place, the hydrogen fourth, and the carbon which is connected to the chlorine second place, and the CH3 group in third place. So we don't have to prioritize a second time over. Now that we've got that locked in 3 dimensions we want to rotate the molecule to put the lowest priority group to the back of the molecule. So let's build this molecule on the left, which has a carbon with a bromine atom and a hydrogen to the back. To the right hand side is a CH3 group. To the left hand side is a carbon with a chlorine attached. So I'm just going to take off the red lead from the one we did before and just automatically put on a chlorine. Just to signify that's the carbon with the chlorine atom attached. So we're looking at the 3 groups of highest priority. Once we've tucked the hydrogen atom, once that low priority hydrogen has been tilted to the back of the molecule so that it's hidden, it's eclipsed behind the stereocenter carbon, we look at the 3 remaining groups attached and look at the direction of rotation. From highest priority 1, we go to the second highest, which is the carbon attached to the chlorine, and then to the carbon with the hydrogen attached. So we're going in a counterclockwise direction. Think about the face of a clock with a ticking hand. If that ticking hand was going backwards like that, that would be kind of stupid for the ticking hand on the clock, going counterclockwise. So to differentiate that molecule from its mirror image molecule, when the 3 highest priority groups are going counterclockwise, we refer to that molecule as the S enantiomer. S for stupid. It's actually for the Latin sinister, but that doesn't really mean anything to people. We're always trying to be snobs, get us by using more technical terms. Because apparently it's the Latin for left. Why couldn't we just use the English for left? Most people do. Again, with that lowest priority group, the hydrogen, with the hydrogen tucked to the back of the molecule, we can look at the mirror image just by moving the carbon chlorine groups and the methyl groups around. So switch them on your molecule. So now that you have the mirror image, with that hydrogen tucked to the back, the 3 highest priority groups going from highest to third place, we're now moving in a clockwise direction for the 3 groups. And when those 3 groups from first to second to third, when they go in a clockwise direction, this is for the rectus or R enantiomer hand on the clock ticking in a clockwise direction, that's the right way for the hand to tick, and not the stupid way. The three highest priority groups counted clockwise, it's the R. It's counted counterclockwise, it's the S.